Well, a really foundational concept in physics, the Born approximation. If you're dealing with how things scatter particles, waves, hitting some kind of potential, maybe an electron off an atom or light through a material.
Yeah, this method is pretty central.
It really is.
That's right. The Born approximation, it gives us a really powerful way to sort of get a handle on these scattering situations, especially when the interaction isn't, overwhelmingly strong.
Or the particle's moving fast.
Or the particle is zipping through at high speed. Exactly. It's a real workhorse in quantum mechanics, condensed matter, optics. You see it everywhere.
And the core idea, reading through your sources, it's actually kind of beautifully simple, isn't it?
It is, at its heart.
It just assumes the original wave, the incoming one, it doesn't get massively changed by hitting the potential.
Right.
The scattered wave is treated more like a small ripple, a perturbation on top of that first wave.
Precisely. And that assumption lets us tackle what's usually a really thorny problem solving the full scattering equation. We can break it down.
Into steps.
Into simpler steps, yeah.
Yeah.
This leads to what's called the Born series.
Yeah.
And the very first step, the simplest useful piece you calculate, that's the first Born approximation.
And often that's enough.
Often it gives you really good insight, yeah.
Okay, so our mission for this deep dive, let's unpack these sources, figure out what this approximation is, peel back the layers on how we get to it, work out when you can actually, trust it.
Good point.
And maybe most importantly, see what it tells us about how these potentials actually shape the scattering we observe.
Sounds like a plan. Let's dive in.
Yeah.
So to really get the Born approximation, we kind of have to start with the basic scattering picture itself.
Okay.
Imagine a particle, right? Described by its wave function. It's coming towards some region in space where there's a potential, let's call it V of R.
Right, VR. And we want the wave function everywhere, the one that satisfies the Schrödinger equation with that VR in it.
Exactly. But actually solving that.
That's the hard part.
That's the hard part. It can be incredibly difficult unless the potential is, super simple.
Like a square well or something.
Something like that, yeah. The wave function we're hunting for needs to describe the particle before it hits the potential, and then after it interacts, both the part that went through and the part that's scattered.
Okay. And far away from the potential, what does it look like then?
Well, far away, the solution looks like the original incoming wave. Usually we picture that as a simple plane wave plus an outgoing spherical wave.
The scattered bit.
That's the scattered bit, spreading outwards.
And that spherical wave, it has some kind of factor on it, right? The scattering amplitude?
That's it.
Yeah.
F, the scattering amplitude. That's the star of the show in scattering theory. Your sources definitely highlight this.
Because the cross-section, what you actually measure.
Right, the differential cross-section, like how many particles bounce off into this particular angle versus that angle that's directly related to the magnitude squared of F.
So find F, and you basically understand the scattering pattern.
You've got the key, yes. But finding F when the Schrödinger equation is tough, that's where we need another approach.
Okay.
And this is where mathematicians were clever. They reformulated the problem, turning the differential Schrödinger equation into an integral equation.
The Lippmann-Schwinger.
An integral equation. Okay, conceptually, what's that representing?
Think of it like this. The wave function at any single point is the sum of two things. First, the initial incoming wave, what you started with.
Okay.
Plus, the contribution from the potential acting everywhere else. It's like each little bit of the potential acts as a tiny source, spitting out scattered waves.
And the integral sums up all those tiny contributions.
Exactly. It sums them all up to give you the total scattered wave. The equation uses something called the Green's function.
Ah, yeah, I remember that. Which basically describes how a wave disturbance travels from one point to another in empty space.
Okay, so the Lippmann-Schwinger equation says total wave, incident wave, plus this big integral involving the potential and how waves travel. But hang on. Doesn't the unknown wave function, the thing we're trying to find, appear inside that integral too?
Ah, you spotted the catch. Yes, it does.
So we're kind of back where we started. You need the answer to calculate the integral part of the answer.
Exactly. It's self-referential, which makes it hard to solve directly. And this is where the Born approximation provides a way out. It uses iteration.
Iteration, like start with a guess.
Start with a simple guess for the wave function inside that tricky integral.
And the simplest guess would be just the original incoming wave, like pretending no scattering has happened yet to influence the wave inside the potential.
That is precisely the first step of the Born series. You make that assumption. just as a starting point. Assume the wave function inside the potential zone of influence is basically just the incoming plane wave. You substitute that simple wave into the integral on the right-hand side of the Lippmann-Schwinger equation.
And then you calculate that integral.
You calculate it, and what you get out is the first approximation to the full wave function, the one that includes the scattered part. That is the first Born approximation.
I see. So you're calculating the scattered wave, but you're doing it based on the assumption that the potential is weak enough, or the interaction quick enough, that it doesn't really mess up the wave while it's interacting.
That's a great way to put it. It's like assuming each bit of the potential only sees and scatters the original incoming wave, not a wave that's already been bent out of shape by other parts of the potential.
So the first Born approximation is essentially boiling the scattering down to a single, simple interaction event between the initial wave and the potential, just summed up over the whole potential region.
Perfectly said. And if that basic assumption holds reasonably well weak potential, high energy, energy, this single interaction picture gets you surprisingly close to the real answer.
Could you do it again? Take that first approximate answer and plug it back into the integral.
You could. That would give you the second Born approximation, which includes effects of two interactions. You can generate the whole Born series this way.
But the first one is the most common.
By far.
Yeah.
It often captures the essential physics and gives the key insights we need.
Okay, now the cool part you mentioned, once you have this first Born approximation for the wave function, you need to extract the scattering amplitude f from it.
Right. You look at the form of the scattered part of this approximate wave function far away from the potential, where it should look like that outgoing spherical wave times f.
And when you do the math, comparing the Born result to the expected form, you find FB, the Born scattering amplitude.
This is where the magic happens, just like your sources say. It turns out FB is directly proportional to something quite specific.
Oh, okay.
It's proportional to the Fourier transform of the potential VR.
Whoa, hold on. The Fourier transform of the potential?
Yes. Evaluated not just anywhere, but specifically with respect to the momentum transfer.
Momentum transfer. Right? That's the change in momentum of the particle, isn't it? The difference between its final momentum vector, kf, and its initial one, k.
Exactly. Let's call that difference vector q. So q equals kf key. The first Born amplitude, fb, is proportional to v tilde q, where v tilde is the Fourier transform of v evaluated at that specific momentum transfer q.
Okay. FB related to V tilde Q. What does that actually mean? What's the physics there?
This is the really powerful insight. A Fourier transform, what does it do? It breaks down a function here, the potential shape in space, into its different spatial frequencies.
Like decomposing sound into different musical notes?
Sort of like that, yeah.
Okay.
High spatial frequencies correspond to sharp changes or fine details in the potential. Low frequencies correspond to broad, smooth features.
Okay.
Now, scattering involves a change in momentum, q. A large momentum transfer, a big Q, means the particle scattered at a large angle. Its direction changed a lot.
Right.
This large Q scattering probes the high spatial frequencies, the sharp details of the potential. A small momentum transfer, small q, means it scattered only slightly, mostly forward. This probes the low spatial frequencies, the large-scale smooth features of the potential.
I see. So by measuring how many particles scatter at different angles, which corresponds to different momentum transfers q, you're essentially using the scattering process to read out the Fourier components of the potential.
Exactly. You're mapping the potential structure in frequency space or momentum space. It provides this incredible direct analytical link between the potential shape and the resulting scattering pattern you observe.
Wow. Okay, that makes sense why it's so useful in things like crystallography.
Absolutely. In crystallography, electron microscopy, neutron scattering, you bombard a material with waves or particles. You measure the diffraction pattern where things scatter.
Which tells you about the momentum transfers.
Which, through this Born approximation and the Fourier transform relationship, tells you about the spatial arrangement of atoms, the periodic potentials within the crystal. It's a direct link.
But you said this link, this approximation, only holds under the right conditions. What are they again?
It really comes back to that core assumption we started with.
Yeah.
The wave function inside the potential isn't too different from the incoming wave.
Right, the perturbation is small.
Yeah. And your sources spell out when that's likely true. Generally, it holds when the potential itself is weak in some sense.
Okay.
Or when the incident particle's energy is high.
So if the potential is really strong, it's going to significantly bend or distort the wave function as it goes through, messing up that initial assumption.
Totally. And if the particle's moving very slowly, low energy, well, it spends more time feeling the potential's influence.
Giving the potential more chance to change the wave function.
Exactly. The Born approximation, remember, is basically a single-hit picture. The original wave gets deflected once. It breaks down if the potential is strong enough or the interaction long enough to cause multiple significant deflections or really warp the wave.
So it's good for, say, fast electrons scattering off a relatively weak atomic potential, but maybe not so good for slow neutrons interacting strongly with a nucleus, or situations where a particle could get trapped for a bit, like a resonance.
Precisely. Those more complex scenarios, strong binding, low-energy collisions, resonances where the particle hangs around, they need more sophisticated methods. Methods that can handle the wave function being drastically changed or involve multiple scattering events.
Your sources also threw in the term not unitary. Can you unpack that quickly? What does unitarity mean here?
Yes. So in quantum mechanics, total probability has to be conserved. Whatever goes in must come out, one way or another.
Makes sense.
The scattering process is described by something called the S-matrix, which connects initial states to final states. For a probability to be conserved, this S-matrix must be unitary. Simple approximations, like the first-born approximation, they don't always guarantee this property mathematically. You might find that the probability calculated flowing out in all scattered directions doesn't quite perfectly add up to the probability that flowed in.
Huh. It's like a leaky approximation.
Kind of, yeah. It's an artifact of not capturing the full complexity of the wave interaction everywhere. More exact methods preserve unitarity.
Okay, clear limitations then, but the upsides. We talked about that amazing Fourier transform insight. What else?
Well, sheer simplicity is a huge one. Actually calculating that Fourier transform integral is often way, way simpler than trying to solve the full Lippmann-Schwinger equation directly or using other, more exact but complicated methods, especially if the potential isn't nice and spherically symmetric.
And that analytical link just gives you immediate physical intuition, right?
Absolutely. You can almost just look at the potential, think about its shape, and get a feel for where particles are likely to scatter based on that Fourier connection. It gives you a direct snapshot.
Let's talk examples. Your sources mentioned the Yukawa potential. That's like a screened Coulomb potential, falls off exponentially.
Exactly. It's like e to the minus alpha r divided by r. It's used a lot in nuclear physics, for instance.
Yeah.
Applying the first-born approximation to Yukawa is a standard calculation.
And what does it give?
It gives a scattering amplitude f that goes like 1 over q squared plus alpha squared, where q is the momentum transfer magnitude and alpha relates to the range of the potential.
Okay, so the cross-section depends clearly on the angle through q and the potential's range through alpha.
Yep, it shows that nice dependence, wider angle scattering, bigger q, falls off faster.
And then the big one, the Coulomb potential, just 1r, like between electric charges.
Right. You can think of Coulomb as the limit of the Yukawa potential as that range parameter alpha goes to 0 in infinitely long range.
Okay, and applying the first-born approximation there.
You basically set alpha to 0 in the Yukawa result, and you find the Born amplitude FB is proportional to 1 over q squared.
1 over the momentum transfer squared. And when you convert that amplitude into the differential cross-section...
You work through the kinematics relating q squared to the scattering angle theta.
Oh, tell me.
And you get a cross-section proportional to 1 over sine to the power of 4 of theta over 2.
That's the Rutherford scattering formula.
That is the celebrated Rutherford formula. But here's the absolutely mind-bending part, which your sources correctly flag.
Yeah.
We just derived it using the first-born approximation. An approximation we know is based on assuming a weak potential or high energy, a single interaction.
Right. It shouldn't be exact.
But for the pure 1R Coulomb potential, the first-born approximation calculation gives the exact quantum mechanical result.
Wait, what? How? The approximation is exact.
For this specific potential, yes. It's deeply weird and fascinating. It turns out that for the 1 potential, all the higher-order terms in the Born series, the second Born, the third, all the corrections you'd normally expect,
They cancel out.
they happen to sum up to 0. Or, rather, they only contribute an overall phase factor to the amplitude, which doesn't affect the cross-section. It's a specific mathematical miracle of the 1 potential.
So the simple approximation accidentally, or maybe not so accidentally, captures the full answer for Coulomb scattering.
Exactly. And even stranger, that quantum result from the first Born approximation happens to be identical to the result you get from a purely classical calculation of orbits, which is what Rutherford originally did.
That is Wild. So for most potentials, Born is a useful first guess. Maybe okay if conditions are right. But for Coulomb, it just nails it.
It nails it. It really highlights how sometimes the simplest approximation, based on fairly broad physical intuition, can have a mathematical structure that perfectly captures the essence of a particular interaction, even if we didn't expect it to.
Your sources also touched on applying this. Electron scattering, neutron scattering, using this Born-Fourier link to figure out material structures.
Oh yes, absolutely. That's a core technique. You measure the diffraction pattern, you essentially measure the squared amplitude as a function of momentum transfer q, and using the Born approximation framework, you work backwards via the Fourier transform to deduce the structure VR of the material that caused the scattering. It's theory directly informing experiment.
Okay, so let's try and wrap this up. Thinking back through this deep dive on the Born approximation based on the source material.
We started with the basic quantum scattering problem, the Schrödinger equation, which is tough to solve directly.
Right. And saw how that leads to the Lippmann-Schwinger integral equation, which is mathematically equivalent but still tricky because it's self-referential.
Then we introduced the Born approximation as a way to break that loop, using an iterative approach.
Yeah.
We focused on the first step, the first Born approximation.
Which relies on that key assumption. The incoming wave isn't drastically changed by the potential. Scattering is treated like a single, small perturbation. And the payoff for that simplification was huge. We found that the scattering amplitude in this approximation is directly tied to the Fourier transform of the potential itself.
Yes, specifically the Fourier transform with respect to the momentum transfer, Q. That gives this amazing window into the potential spatial structure just by looking at how things scatter.
We definitely covered the buyer beware parts too, the conditions where it's valid. Generally needs weak potentials or high energies.
And acknowledged its limits. It struggles with strong forces, low speeds, things like resonances, and it isn't strictly unitary.
But we saw its power in examples like the Yukawa potential, and especially that incredible case of the Coulomb potential.
Where the first Born approximation, against all odds, gives the exact Rutherford scattering result.
So the big takeaway seems to be, it's a method prized for its simplicity, giving real analytical insight, especially that Fourier connection. It provides a clear path to meaningful results and a physical picture, as long as you're aware of when you can trust it.
Well put.
So, thinking about all this, especially at that point about the Coulomb potential, the first Born approximation simplifies things massively, right?
Right.
Treats it as one interaction, approximates the wave inside. Yet somehow, for that specific one potential, this rough and ready first step gives the exact answer, while for others, it's just, well, an approximation that can fail quite badly.
Yeah.
What does that make you wonder about approximations in physics, it feels like? It shows the surprising power you can sometimes get from simplifying complexity. But it also suggests there must be subtle clues maybe hidden in the mathematical form of the problem itself, like the smoothness or the long range of the one potential, that tell you when a simplification isn't just convenient, but might actually capture something profoundly true about the system. It's a really interesting tension, isn't it, between simplifying and getting it exactly right.